Is the Word file visible? Can you see it?
Yes.
Okay. So we have started deliberating on discrete time systems. The first type of discrete time system that I have started with is the discrete time differentiator. And we approximated the derivative by what is known as the backward difference relation given by this equation 2. So this is the expression. In a general form, you can write it as yn equal to a0xn plus a1xn minus 1, where a0, coefficient a0 of this backward difference relation, it's 1 by tau. Tau is the sampling interval or sampling period, and a1 is minus 1 by tau. So it is customary to represent this algorithm by this pictorial depiction. So this pictorial depiction is known as the structure for the algorithm. All right, structure for the algorithm. So what does this depiction represent? What it represents is that at every instant, the input sample xn at the current instant, current sampling instant, it's multiplied with a coefficient a0 that is retrieved from a memory location. Now, if you have xn here, here you have xn minus 1. This block with tau inscribed, this is called the unit delay element. It delays the input sequence by one sample. So if you have xn here, here you have xn minus 1. So at every sampling instant, xn is multiplied with the constant a0 retrieved from some memory location. Xn minus 1, which is already stored, it is multiplied with coefficient a1 retrieved from another memory location. And these two products, they are added to generate the output at the current instant. All right. So that is the depiction of the algorithm. So this is a causal discrete time differentiator. So if you start with n equal to 0, at n equal to 0, you have x0 here. Here you are supposed to have x minus 1, but because it's a causal system, x minus 1 will be 0. Because we are dealing with causal system and therefore causal sequences, x minus 1 will be 0. So x0 is multiplied with a0, and because this is 0, the product here will be 0. So a0 into x0 will give you y0. At n equal to 1, you have x1 here, you have x0 here. So x1 is multiplied with a0 retrieved from some memory location. x0 is multiplied with a1 retrieved from some memory location. And these two products are added to get y1. In a similar manner, at n equal to 2, you have x2 here and you have x1 here. So x2 into a0 plus x1 into a1 will give you y2. In this way, the computation will go on. All right. Now, if you take the z transform of both sides of this equation, z transform of the both sides of this equation, and then you divide yz by xz, what will you get? a0 plus a1 z to the power minus 1, which is 1 by tau into 1 minus z to the power minus 1. So this is the transfer function. We call it the z transfer function of the differentiator. Z transfer function of the differentiator. All right. It's 1 by tau into 1 minus z to the power minus 1. As you have the transfer function in the Laplace domain for the continuous time systems, you also have the transfer function in the Z domain for discrete time systems, discrete time LTI systems. Now, because this is the transfer function, recall what's the transfer function of a continuous time differentiator? Transfer function of a continuous time differentiator. Say if I label it as G prime S, what will be the transfer function of an ideal continuous time differentiator? Speak out. It's a very basic thing. If you have a continuous time LTI system that performs differentiation of the input signal, if you take the Laplace transform of the output and the Laplace transform of input and divide the Laplace transform of the output by Laplace transform of input, what will you get?
Sir,
S,
S.
right?
Yes, yes.
So transfer function for an ideal continuous time differentiator is S. So if that is the case, then if you just compare these two expressions, G prime Z equal to this expression and G prime S equal to S, then we have this equivalence. S is approximately equal to 1 minus Z to the power minus 1 by tau. All right. So write it down, then I'll proceed. That approximate relation between S and Z, it will be useful in filter design or designing any discrete time LTI system. Because if you want to use the exact expression, it's comparatively difficult. In terms of hardware, how is this? How will the unit delay element be implemented? It's nothing but a shift register that delays the input sample by input sequence by one sample. Often the unit delay element is represented by a box with Z to the power minus 1 inscribed. Instead of tau, often Z to the power minus 1 is also there. You know why? Because delaying a certain sequence by one sample means in the Z domain, delaying the Z transform of the input sequence, I mean, multiplying that Z transform of the input sequence by Z to the power minus 1. So that's why often instead of tau, Z to the power minus 1 is also written here. Here there is some typing error. It should not be capital Z, it should be small z. A1 Z to the power minus 1. It should be small z. After noting this equivalence, we will move on to discrete time integrators. Done.
Done.
Now consider a discrete time integrator. Recall that for a causal continuous time integrator, this is the expression. So at every instant t, the output of this continuous time integrator is the area covered by the input signal from 0 to the current instant. All right. Now, if you want to perform this integration digitally or using a discrete time integrator, then first task will be to sample this analog signal xt. So that is the sampler. Tau is the sampling interval or sampling period. You get x and tau here. So the task of the discrete time integrator will be to find out the integral of xt up to the current instant. It means determining the integral of xt up to the current sample value, up to the current sampling instant n tau or n. All right. That means the area under xt from 0 to n tau. That should be the output. What are the information available to the discrete time integrator? Only the current input sample and, if required, previous input samples and the knowledge of tau. So these are the only things that are available to the discrete time integrator. With these things, the area has to be determined. So y and tau will be xt prime dt prime. It's just integrated over 0 to n tau. Now that integration over the interval of integration, you can split it up into two parts. You can split it up into two parts. One will be the integral of xt prime from 0 to n tau minus tau. And second one will be the integral of the function xt prime from n tau minus tau to n tau. Because y n tau is represented by that integral, what will this integral represent? Y n tau minus tau, because the integration extends from 0 to n tau minus tau instead of n tau. So if this is n tau, that one will be y n tau minus tau, meaning the already computed output value at the immediate past sampling instant. So now the task remains to represent that area from a knowledge of the input sample and a knowledge of tau. So how to calculate that area? You cannot calculate it exactly. Some approximations have to be made. So first possibility is that, so what you have to find out is this area, all right. This area is required, but exact method of, obtaining this area exactly, that is not possible. So this area is approximated by the area of this rectangle. You have studied about rectangular integration, isn't it? So the second term on the right hand side that we are considering, it can be approximately represented by x n tau into, with height is x n tau into this base, which is tau. So tau into x n tau. All right. So that can be approximated by tau into x n tau. Smaller is the sampling interval, better will be the approximation. So y n tau becomes now y n tau minus tau plus tau x n tau, or yn will be yn minus 1 plus tau into xn. If you can keep the case general, yn will be a0 xn plus yn minus 1, where this coefficient a0 is tau. So what will be the pictorial depiction of this algorithm? This is the case. All right. You have xn here. A0 is stored in some memory location, and the value of yn is fed back to this adder. It's delayed and then fed back through this adder. So if you have yn here, here you have yn minus 1. So every unit delay element represents a storage, a memory location. All right. Every unit delay element simply represents storage. If there is a single unit delay element, a single value of the sequence that will appear at the input is kept stored here. So what is kept stored in this case will be the already computed output value at the immediate past sampling instant. So at every instant, what the integrator does is that the sample value xn is multiplied with a0. So this product is added to yn minus 1. And this addition, this sum gives yn, the output, desired output sample at the current instant. So at n equal to 0, you have x0 here. x0 is multiplied with a0, where a0 is retrieved from some memory location. What is the sample that will appear here? It will be, because we are considering n equal to 0, this sample is yn, this sample is y minus 1. Because we are considering causal system, y minus 1 will be 0. So y0 will be simply a0 into x0. Consider n equal to 1. Here you have x1. Here you have y0, which is already computed. All right, that is kept stored. So x1 is multiplied with x0, and then it's added with y0 to give y1. At n equal to 2, x2 is multiplied with a0, and then what is added to it? y1 to get y2. In this way, the computation proceeds. So this feedback element is present here, feedback path. If you take the z transforms of both sides of this equation, what will you get? Xz will come out as, yz will come out as a0 xz plus z to the power minus 1 into yz. Because you have a delay here. So yz, if you take the z transform, yz will be there. Here you will have z to the power minus 1 into yz, which follows from the shifting property of z transform, plus tau, which is a constant, into xz. All right. Tau is equal to a0. We are considering it's equal to a0. So this integrator is called backward rectangular integrator. There is another variant of rectangular integration that I'll consider just after this one. So the transfer function for this so-called backward rectangular integrator is as indicated there, yz by xz, which is a0 divided by 1 minus z to the power minus 1. That means tau divided by 1 minus z to the power minus 1. All right. Now, what is the transfer function of a continuous time integrator? Tell me.
1 by s.
1 by s. 1 by s.
1 by s. So comparing the continuous time transfer function for the integrator with the transfer function in the z domain for this backward rectangular integrator, we get 1 by s is approximately equal to tau divided by 1 minus z to the power minus 1. That means s is approximately equal to 1 minus z to the power minus 1 by tau. Same relation as we have obtained in case of the differentiator. Same relation. Write it down. That is the basic expression, equation 6. Now we will consider different ways of approximating the second term on the right hand side of equation 6. The first approximation has been considered. What's the second approximation that we'll see? So this is the case. This axis is t prime, that axis is x t prime. The blue vertical lines, they are the samples of x t prime. Have you drawn the figure?
No, sir. Can you go a bit up? Okay, sir.
Yes. Do you have any question? Now the rectangle that I have drawn, is this the only possibility of drawing the rectangle? Is there any other possibility of drawing the rectangle?
Tau into x and tau minus tau.
Right. That is the second approximation, second possibility.
But sir, all these are approximate, not exact.
No, they are not exact.
Oh, okay.
You can't obtain the exact. You have to obtain these
Right.
approximations. Whenever you are performing this numerical integration, you have to do some approximation.
Okay, sir. Thanks.
Because the information between two consecutive input samples that is not known to you.
Mm-hmm.
Therefore, you have nothing else to do.
Yes. Got it.
I call it the backward rectangular integration. And the other in a rectangular integrator that will be called the forward rectangular integration. The backward rectangular integration is the common usage. But you can also come across this forward rectangular integration. And that's little bit less, but also not rare. In many cases, you will find that forward rectangular integration is also used. So that is the structure for the backward rectangular integrator. One addition and one storage location that is required for implementing this backward, one storage location for the input sample and one storage location for this coefficient. In case of the continuous time integrator, it has a single pole at the origin in the S-plane transfer function. For the transfer function of the backward rectangular integrator, there is 1, 0 at the origin of the Z-plane and one pole at Z equal to 1. So S is approximately equal to 1 minus z to the power minus 1 by tau. Area of that rectangle as tau into x n tau minus tau. That is the second possibility. Then the second term on the right hand side of equation 4. Was it equation 4? Let me just see. No, it was equation 6, sorry. This was equation 6. Just 1 minute. So here, change it to equation 6. So the difference equation is as shown. So there is a delay element, unit delay element required for yn tau as well as for xn tau. So this method, this particular rectangular integration technique, it utilizes the already occurred input sample and already computed output sample at the immediate previous sampling instant. So those values are used. Current input sample is not used for this second type of rectangular integration. What will happen to the transfer function in this case? What will be the difference? It will be same as the transfer function of a backward rectangular integrator, but there will be a z to the power minus 1 term, extra term in the numerator. So the amplitude response, it will be same. Amplitude response, that will be same for both the cases. আঁকা হয়ে গেছে?
Done, sir.
হয়েছে?
Done, sir.
So that is the alternate first order difference equation for discrete time integrated using forward rectangular integration. Now apparently this is the block diagram representation of the structure, and this structure you will find in many textbooks. But so far as implementation is concerned, just try to observe here that if this is the structure, then what is required is that xn has to be multiplied with a0, and to it yn has to be generated, yn has to be added, and then this summation a0xn plus yn, it is to be fed to a unit delay element to get yn. Therefore, according to that structure, for getting yn, you have to utilize the value of yn. So that type of a structure will not do for implementation. For implementation, what will be the structure? This one. This is the structure. Here you have yn minus 1. Here you have xn, here xn minus 1. Now you can definitely add yn minus 1 with a0 xn minus 1 to get yn.
So in this structure, xn a0 and yn is directly firstly added, then delay. But in this equation, first delay is added, but yn minus 1 is added. So, sir, in this structure, xn a0 plus yn is directly added.
Won't it result in the same thing? If you consider here, what will be the output of this adder? A0 xn plus yn. Then what will be the output here? Here there is a simple unit delay. You have here A0 xn plus yn. So here you will have, you are supposed to have A0 xn minus 1 yn minus 1. All right.
Okay. Achha.
But because of the reason that I have cited, this is not feasible.
Okay, okay.
But because this structure is there in many textbooks, I have first drawn it to show that this is not feasible. And this is the transfer function of the forward rectangular discrete time integrator. You have simply an extra z minus 1, z to the power minus 1 term here in the numerator. That is a structure that can be realized in practice. Have you done it?
Done.
Now for the integration, for the second term on the right hand side of equation 6, a better approximation from your knowledge of numerical integration will be to represent that area by the area of a trapezium. So this is the case. So that area is approximated by the area of this trapezium. You can easily find out the area of the trapezium in terms of xn tau minus tau, and tau. So this is the area of the trapezium, tau by 2 times sum of those two sides. This is x n tau, and this one is x n tau minus tau. Sum of the parallel sides times tau by 2. So in this type of integrator, the yn minus 1 term is there, the xn term is there, the xn minus 1 term is also there. Withdrawn it.
Yes.
So this is the final difference equation or difference relation. A difference equation relating the output and input sequences of a trapezoidal integrator. Those two coefficients, the coefficients of xn and xn minus 1 term, they are same. If you compare the transfer function of a continuous time integrator with that of this trapezoidal integrator, that will result in another approximate relation between S and Z, but it will be a better approximation. A0 and A1, they are same, tau by 2. So the structure of this algorithm is shown there. All right. Here, there are 2 unit delay elements required. 2 numbers, 2 input adders, and 2 numbers unit delay elements. That means 2 storage locations are required for storing xn minus 1 as well as yn minus 1. Here, a1 xn minus 1, that is stored. So I am not narrating how the computation is going on because I have already pointed out. So you must be able to understand on your own, starting from n equal to 0, how is the computation progressing. In this case, if you take the Z transform of both sides of the difference relation representing the integrator, you come up with another transfer function of the discrete time integrator. So that is the expression for the transfer function of the trapezoidal integrator. Tau by 2 times 1 plus z to the power minus 1 divided by 1 minus z to the power minus 1. Now here, if you just proceeding in a similar manner as we did in case of the rectangular integrator, what will be the approximate relation between S and Z? 1 by S, if you compare it with this trapezoidal integrator transfer function, 1 by Z, it will be approximately equal to this tau by 2 times that function. Or S will be approximately equal to just the reciprocal, 2 by tau times 1 minus z to the power minus 1 divided by 1 plus z to the power minus 1. The equivalence between S and Z that we obtain here, is that relation known to you? Have you come across that relation earlier?
Sir, bilateral Z
Bilinear transformation.
Z.
Bilinear transformation. It is called bilinear transformation, also known as Tustin transformation. Recall that right at the beginning, when I considered the exact expression between S and Z, S was 1 by tau times natural logarithm of Z. So natural logarithm of Z was expanded into an infinite series and it was truncated after the first term. So that resulted in the same bilinear transformation relation. There I pointed out that I didn't cite any logic behind truncating the series after the first term. Now here is that logic. So this is the bilinear transformation or Tustin transformation relation. Why it is called bilinear transformation? Because in this transformation relation, both in the numerator and denominator, you have linear function of z. The numerator as well as the denominator is linearly related with z. So that's why it's called bilinear transformation. So that was about discrete time differentiator and discrete time integrator. It's my duty to move on to a generalized treatment of discrete time LTI system, as we did in the case of continuous time LTI system in your signals and systems course. So to understand that, the generalized representation of a discrete time LTI system, we must note certain facts. So just note certain facts, then you will understand how to represent, how to have a generalized representation of a discrete time linear time invariant system. So here I consider that we have a DT-LTI system, and this DT-LTI system is processing an analog signal ST. So your first task will be to sample this signal or digitize this signal. Tau is the sampling period. So at the after sampling, you have this sequence Sn tau or Sn. It is processed by the DT-LTI system, which generates Zn tau or Zn. All right, this has nothing to do with Z transform. This Z is a variable, dependent variable of this independent variable N. Now, I will consider a few cases. If the nature of the DT-LTI system is such that it performs first order differentiation of ST at the sampling instance, then what will be the relation between Zn and Sn? You know that Zn and Sn will be related through this difference equation, where A01 is 1 by tau and A11 is minus 1 by tau. That we have already seen. So this is the backward difference relation. Next, consider as if the DT-LTI system is such that it performs the second order differentiation of ST at every sampling instant. So Zn tau represents the second derivative of ST at every sampling instant n tau. Then how will Zn and Sn be related under such a condition? I hope you have written it. So if this is the case, Zn tau is the second derivative of ST at the sampling instance. So second derivative of ST at the sampling instance, it can be replaced by, if you consider the backward difference relation, the first derivative of st at t equal to n tau minus the first derivative of st at t equal to n tau minus tau divided by tau. Now this first derivative of st at t equal to n tau, it is again using the backward difference relation Sn tau minus Sn tau minus tau divided by tau. The first derivative of st at t equal to n tau minus tau, if you replace it with this backward difference relation, it will be Sn tau minus tau minus Sn tau minus 2 tau divided by tau. So difference of these two terms that constitute the numerator of Zn tau. In the denominator, you have tau. So here you will have a tau here. So on simplifying this expression, you will get Zn as A0 to Sn plus A1 to Sn minus 1 plus A2 to Sn minus 2, where A02 and A22 will be 1 by tau square and A12 will be minus 2 by tau square. If you simplify it, you will get these values. So the first order derivative, it was approximated by a first order difference relation. The second order derivative, it is approximated by a second order difference relation between Zn and Sn. Similarly, if you have the DTLTI system such that the DTLTI system will perform the third derivative of ST, third order differentiation of ST at t equal to n tau, then the relation between Zn and Sn will be given by a third order difference relation, a difference equation. A03 Sn, A13 Sn minus 1 plus A23 Sn minus 2 plus A33 Sn minus 3. You can easily obtain the values of A03, A13, etc. in terms of tau. Proceeding in this way, if you have Zn tau as the ith derivative of St at t equal to n tau, then the relation between Zn and Sn will be an ith order difference relation. Zn tau is the ith derivative of st at the sampling instance. So that is the difference relation. A0 I Sn, A1 I Sn minus 1, A2 I Sn minus 2, in this way up to AII Sn minus I. So we can just use this knowledge to represent a discrete time LTI system in general, any general form of DT LTI system by a constant coefficient difference equation between the relating the output to the input sequences. We start from a continuous time LTI system. What is the most basic mathematical model of a stable and causal CT-LTI system? In the time domain, it is obviously the differential equation representation. A constant coefficient differential equation representation relating the output to the input. That is the most basic mathematical model of a stable and causal CT-LTI system in the time domain. So this is equation 1 is the nature of the differential equation relating the output yt to the input xt. Here, the highest order of the derivative on the right hand side is capital M, and on the left hand side, the highest order of the derivative of yt, that is capital N. For Bibo stability of the system, M has to be less than equal to capital N. AI, BI, these are the constants. That's why we call it constant coefficient differential equation. Capital N gives the order of the system. Now you are ordinarily not accustomed to this type of differential equation representation, because in case of the practical systems that you have studied, almost always on the right hand side you have what do you have on the right hand side? A term involving the input only. So on the right hand side, usually you have this B0 xt term, only this B0 xt term. All right. For most of the systems that you have studied, perhaps. হয়েছে? What will be, how will you form the discrete time equivalent of this system? How will you form the discrete time equivalent for this system? For forming the discrete time equivalent of this continuous time LTI system, what you have to do, we have to replace on the left hand side, we have to replace each or derivative of yt by a difference relation, isn't it? Each derivative of yt, first derivative has to be represented by a difference relation, constant coefficient difference relation. Second derivative of yt, that also has to be represented by a constant coefficient difference equation, etc. Similarly, on the right hand side, each derivative of xt has to be replaced by a constant coefficient difference relation. As a result, what will happen to the equivalent DT-LTI system? So this is the discrete time LTI system performing the same job as the earlier earlier continuous time LTI system, performing the same task, equivalent task. So xt has to be sampled fast. You have a causal signal xn. The output of the discrete time system is yn. So if you want to, if this discrete time LTI system has to mimic the operation of the continuous time LTI system, in this summation of the differential equation representation, each such derivative has to be evaluated at t equal to n tau on the left hand side as well as on the right hand side. So that's why what I have stated is that each derivative has to be replaced by a constant coefficient difference relation. What will be the net effect? What will happen to the left hand side? What will happen to the right hand side? The left hand side will become summation over I equal to 0 to n alpha I yn minus I, and right hand side will be I summation over I equal to 0 to capital M beta I into xn minus I. Where alpha i's and beta i's, these are constants. So in case of the DT-LTI system, we have this constant coefficient linear difference equation representation relating the output yn to the input xn. For the case when capital N is not equal to 0, if N is not equal to 0, what will be the, what can you do here? Alpha 0 yn, the term for I equal to 0, alpha 0 yn can be kept to the left hand side. Other terms in yn minus I can be shifted to the right hand side. So what do you have? You have a difference equation represented in that manner. Let's stop here.
Sir, can you go up to the diagram, the discrete
Yes.
time LTC? Yes.
Let's stop here today. Have you written it? Please let me know when you complete writing. Have you completed writing?
Yes.
Yes, sir.
So, okay, let me know when you can have the next class. Discuss among yourselves and let me know later. So I'm shutting down the computer. All right.
Okay, sir. Thank you.
Thank you.